This is the Chapter 8 Chem 101 Spring 2021 quiz. Which species is a diprotic acid? Since we're asking for an acid, we're looking for that material that has an H in front of it and is a neutral compound. Di means two. Pro deals with the H plus, proton, diprotic. So does A have two H's in it? Not two OH's, just two H's in it. No, it doesn't. Is H2, hydrogen gas, an acid? No, it's not. Does B have any acidic hydrogen in it? Yes, it does, but it only has one. Answer here is carbonic acid, H2CO3. There are two hydrogens listed first. It is a neutral compound. This is a diprotic acid. Number 2, which species can act as a Brunstad-Lowry acid? Brunstad-Lowry acids are those things that have an ionizable hydrogen. Therefore, they have to have hydrogen as the first element in the formula, and they have to be a neutral species. Hydrogen in there anywhere? No. Hydrogen in here anywhere? No. Hydrogen here, yes, but is it the first element in the formula? No. Only one here that has the hydrogen in the formula, first listed neutral compound, HBr. Number 3, which of the following is not an acid-base conjugate pair? So acid-base conjugate pairs differ only by the presence or the absence of a hydrogen. So H2CO3 and HCl3. These two differ by the presence of and the absence of one hydrogen. These are conjugate acid-base pairs. H2O and OH minus, conjugate acid-base pair. These differ from one another only by the presence or the absence of a hydrogen. H3PO4 and H2PO4. So these differ from one another just by the presence or the absence of a hydrogen. NH4 and NH3, those are conjugate acid-base pairs. They differ from one another only by the presence or the absence of a hydrogen. H2SO4 and OH, well, if H2S loses a hydrogen, it becomes SH minus, not OH minus. So H2S is an acid, but OH minus is not the conjugate base of H2S. Number 4, the acid-base neutralization reaction between KOH and H2SO4 gives two products. The mnemonic device that I taught you is an acid and a base react to produce water and a salt. So we have the acid H2SO4, the base, KOH. They produce water. There's the H and the OH. So there's water, and the salt is what is left over. The potassium here and the sulfate. Potassium is +1, sulfate is -2. Therefore, to have a neutral compound, we have to have two potassiums to neutralize totally the sulfate anion. So it is H2O and K2SO4. Number 5, pure water cannot conduct electricity. So why do we have to be careful about electric appliances near water? It is the presence of dissolved ions in water that causes electricity to conduct. So water always has some ions dissolved in it. That's why we can't have or it's unwise for us to have a blow dryer near water or an electric heater or something like that. So water always has some ions dissolved in it. That's why it conducts electricity. Number 6, what is the concentration of the hydronium H plus ions in an acidic solution. pH numerically has to be less than 7. Numerically less than 7. So, if we look at this, this means that our pH is less than 7 here. Here, our pH is greater than 7. So the answer here is E, less than 7. Number 7, which solution is the one that has a hydrogen ion concentration that has a pH of 3.35? So here we see the pH. If you remember in lecture, I said whenever you're doing the logarithmic operation, usually the pH first digit is 1 less than the exponent. So since our first number here is 3, we know our exponent is 4. Well, which one of these has an exponent of 4? That guy right there. So answer to number 7 is C. Number 8, titration of a 25 ml perchloric acid solution requires 21.37 ml of KOH to neutralize it. What is the concentration of the KOH? Let's write the reaction. We have an acid and a base. Products of an acid and a base are water and a salt. HOH, so there is our OH, there is our H. What is left over? The K and the Cl. So that's our reaction. This reaction says that 1 mole of HClO4 reacts with 1 mole of KOH to produce 1 mole of water and 1 mole of KClO4. Let's write some other information down that we have associated with these values in our equation. We have 25 ml of a 0.125 HClO4 solution. We have 21.37 ml of our KOH solution. What is the concentration here? We have one other point of information we've not identified or written down. What does this say? This reaction equation says 1 mole of this reacts with 1 mole of that. That's what the coefficients in front of that say. Well, do we have 1 mole of this? No. Could we walk to or figure out how many moles of HClO4 we do? Yeah, we can do that. We have a volume and a molarity. Molarity is 0.125 moles HClO4 per 1 liter HClO4 solution. That's what the 0.125 molar HClO4 says. Well, do we have 1 liter of it? No, we only have 25 ml. So if we convert that to liters, 0.0250 liters HClO4 solution. Liters HClO4 solution, we're left with moles. what does this equation say? 1 mole of this reacts with 1 mole of that, or 1 mole HClO4 is equal to or consumes 1 mole of KOH. That's what the reaction says. One of these reacts and consumes one of these. So we have a 1-to-1 mole ratio. Well, if we can stick that here, 1 mole of HClO4, 1 mole KOH. Moles HClO4 canceled. Therefore, we are left with our answer in terms of moles of KOH. But it doesn't ask for moles of KOH, it asks for molar concentration. What is the concentration of the KOH? Molarity is defined as moles per liter. Here this allows us to calculate the moles of KOH. Do we have a volume? Yeah, we had 21.37 ml. So we take this numbers of moles of KOH, we put there 0.02137 liters KOH solution. We have moles per liter, so it is 0.0250 times 0.125 times 1 times 1, that divided by 0.02137. Answer here should be 0.146 molar KOH. Number 9. How many ml of a 0.6530 molar NaOH solution are needed to neutralize 25 ml of a 1.02 molar HBr solution? Neutralization reaction is given there. So let's write down the information that we have. How many milliliters? So we're looking to find a volume. How many milliliters of a sodium hydroxide solution? So we're wanting that volume. Its concentration is 0.653 molar. What other information do we have? 25 ml of a 1.02 molar HBr solution. So we've got a volume here, 25 ml, and a concentration here of 1.02 molar HBr. We have one other piece of information. What is it? From the equation, 1 mole of NaOH reacts and consumes 1 mole of HBr. So we have a 1 mole NaOH consumes or is equal to 1 mole HBr. Where are we starting at and where are we asked to go to? We're asked to end up here. Where are we given most information? Right here. The HBr is the only other thing that we have relating in our problem to the NaOH. We have one more piece of information, that the coefficient in front of the NaOH is equal to the coefficient of the in front of the HBr. It is a 1-to-1 mole ratio. So we're wanting to end up here. We start with our HBr. Well, we have 25 ml of an HBr solution that is 1.02 molar HBr. Well, what does molarity mean? 1.02 moles HBr per 1 liter HBr solution. Well, do we have 1 liter of this? No, we only have 25 ml. So let's change that 25 ml of HBr solution to liters. 0.025 liters HBr solution. So liters HBr solution cancel. Now we're in moles. We know that we have 1 mole of HBr for every 1 mole of NaOH. 1 mole HBr, 1 mole NaOH. So we've used that information. We've used both of these. The only bit of information we haven't used yet is this concentration term. It is 0.653 molar. Well, what does 0.653 molar mean? It is 0.653 moles of NaOH per 1 liter of solution. Remember, these terms of molarity can be flipped or inverted. So if we have 1 liter NaOH solution per 0.653 moles NaOH, moles NaOH cancel, moles HBr cancel, liters of HBr solution cancel. We're left with liters of NaOH solution. You're asked to calculate a volume term. Our units are left in terms of volume. Run the math through, we should get the right answer. So it's 0.025 times 1.02 times 1 times 1. Divided by 1, divided by 1, divided by 0.653. So the answer is not provided in any one of these. So the answer here is E for number 9. Last problem, number 10. Buffers are going to be extraordinarily important for your nursing chemistry studies. Buffers are those solutions that can withstand changes to their nature when you add base or acid to them. What they do is that they buffer neutralizes any added acid or base such that the pH of your solution doesn't change that drastically. Small changes in your pH, not from 1 to 2 to 3 to 4 to 5, but 0.1 to 0.2. Small changes. So of these, which will be a buffer pair? A buffer is made up of a weak acid and its conjugate base. So, of your 6 strong acids, HCl, HR, HBr, HI, HNO3, H2SO4, and HClO4, there are your 6 strong acids. If you're asked what the identity of the acid is, if you're asked what kind of acid it is, if you know those 6, you know all the strong acids. By process of elimination, you can identify if it's a strong acid or a weak acid. So the 6 strong acids, HCl, HBr, HI, HNO3, H2SO4, and HClO4. Those are your 6 strong acids. So here we have HI, the strong acid. It's not a buffer. HBr, strong acid, not a buffer. HCl, strong acid, not a buffer. HF. Is that a weak acid? Yeah, it's not one of the 6 strong acids, so this is a weak acid. Is cesium fluoride a conjugate base to HF? Yeah, it is. HF plus cesium hydroxide generates cesium fluoride plus water. So HF acts as your acid there, cesium hydroxide acts as your base. So cesium fluoride is the conjugate base of HF. So the answer here is number D. That's chapter 8. Hope this has made sense. If you have any other remaining questions that I didn't address, please make an call and make an appointment to come to see me during my office hours. Thank you very much. Have a good day.